Hello oceanography students. So this is the second video in the topic of waves, and in the last video you learned about some different terms that we use to describe waves and measurements of waves, and you also learned about what happens as a wave approaches the shoreline. Now we're going to talk about some effects of the shape of the shoreline, effects of interference when two waves combine, and we'll also talk about tsunami. Okay, so when a wave approaches the shore, remember that it feels the bottom and the front wave slows down and the wavelength decreases. Now, most of the time, waves are not approaching the shore perfectly parallel. Lots of times, a wave train is either coming from the north or it's coming from the south. It's coming at an angle, essentially. But when you're sitting on the beach, the waves seem to be breaking parallel to the shoreline. So why is that? Well, the reason is basically that the waves bend or refract. So in this image here we have the land and here we have the water. Each blue line represents an individual wave in the wave train. You can see that the waves are coming from this direction. Okay, they're not coming directly onto the shoreline. But as one side of the wave is in shallower water over here near the shoreline, it essentially slows down and the wave bends. So you have this curved shape of the wave now, right? Where this was the original direction that the wave is coming from, but as one side of the wave is in shallower water, that makes the wave bend, so that the wave is now facing the shoreline nearly parallel, and therefore the waves are breaking nearly parallel to the shoreline. Okay, so the shape of the shoreline is then going to affect what the waves look like, right? So we can see here we have this area where the land is jutting out, and you have this wave train that's coming in at an angle. As one side of a wave touches the shallower part of the water, it is slowed down and bends towards the land. And so you can actually see that happening where the wave is actually bending towards the land. And you should also notice all of this white water that seems to be around where the land is jutting out. So what that means is that the wave's energy is directed at the land that's jutting out, whereas it a lot of the energy is not directed where the land is going in. Okay, so if you have an area on land that has land that juts out, and then you have land that is tucked back in, the wave energy will be directed at the land that is jutting out, because one side of the wave will slow down and turn towards the more shallow area, right? So it turns towards the land that's jutting out. And what that makes happen is basically less energy being directed at areas that are little coves. So what we have here at a headland, we have waves that are crashing and breaking against that headland, whereas in this little cove, this little bay, we have really gentle waves. And so you can have this nice little gentle beach form because of sediment that is being eroded, or rock that's being eroded and transported into this little beach. Okay, so the shape of the shoreline actually affects the wave's energy, where the strongest energy is going to end up being directed at land that's jutting out, and the wave energy is directed away from land that is a little cove. Okay, so we can see that here, in this very secluded area from the wave. So a wave can come in here, and it's basically going to curve towards the areas where the land is jutting out. And so you can see the way that this wave is spread out, it ends up being really gentle. Whereas over here, you can see all these rocks. Now the reason why this is not like nice sandy area is because the waves are directed right at that. Okay, and so that can create a kind of topography like what we see along our north coast, right? If you go out to Point Reyes or anywhere along the beach, what you're going to see is you're going to see areas where land is jutting out, and then you're going to have little nice, more sheltered beaches as well. Where the land is jutting out, the wave energy is directed at it. And so what can happen is that that land over time gets eroded by the wave activity, and pieces of it actually separate. So you can see these rocks that are out here. This used to be part of this land here, but because of all the wave activity, it caused erosion, and therefore you have rocks. And if you go out to our beaches, you will see places where there is land jutting out, and from that land jutting out, you have larger rocks that are going away from it, because those larger rocks used to actually be attached to the land there, or to the cliffside. Okay, now when you're on a beach, a wave comes in and a wave goes back out. Okay, so waves that are coming in, that's called the swash of the wave, and when the wave is going back out, that's called the backwash. Now, this is important because waves carry sediment with them, and also can carry other material that can be deposited onto the beach, or it can be carried off of the beach. Okay, so when a wave comes in, when the swash comes in, some of that water seeps into the sediment, and what doesn't seep into the sediment goes back out as backwash. All right, so if you have slow waves occurring, where you have a wave that comes in, and that wave the water from that wave can seep into the sand, then you're going to have more swash coming in, meaning more water is coming in than water is being taken back out, because some of the water that came in soaked into the sediment rather than rushing back off the beach. But if you have waves that are constant, then what's going to happen is the first wave might have some of its water seep into the beach, but then the second wave isn't going to have water seep into the beach because the beach already has water in the sediment. So the sediment can only take so much water. It doesn't have time to dry out from one wave to the next. And so the swash comes on, and then the same amount of water goes back off of the beach. So that would be a beach that's dominated by backwash. Okay? So essentially, that's what happens in the winter time. So usually in the winter time, a beach is dominated by heavy wave activity. That means that there are constant waves and there are kind of strong waves. And therefore, the sediment doesn't have time to dry out for the next wave to come in and for that water to seep into it. So instead of having some water from the wave seep in, all of the water goes back out. And so heavy wave activity, which is often characteristic of winter environment, heavy wave activity tends to be dominated by backwash, which means material moving off of the beach. So what this can do is actually take sand from the beach and move it off of the beach, and eventually that sand then gets deposited onto a sandbar. Okay, so the waves are coming onto the beach, they're grabbing onto sand, and then as the wave moves back off, the sand ends up falling out of the water and piling up on the bottom, and we have what's called a sandbar that gets created. So you can see this beach, this winter beach, doesn't have any small particles. Instead, it just has the big rocks that are left, because all of the small particles were taken off of the beach. Now this picture here is that same exact beach, but in the summertime. So the summertime is often dominated by light wave activity, which means that you have a wave come onto the beach, and some of the water seeps into the beach, and then the remaining water comes back off. So, and then the next wave that comes on comes back slowly enough that the sediment can actually dry out a little bit, and so that water can seep back into the sediment, and the remaining water goes back out. So what we would say is that summer beaches are dominated by swash, meaning the water coming onto the beach. And therefore, that water coming onto the beach is bringing with it sediment and depositing the sediment onto the beach. So that sandbar that was there in the winter basically gets moved back on to the beach, and you have this nice wide beach that you can lay out and make sandcastles on. Okay, so here I have two pictures of the same beach, right? So one of them is in summer and one of them is in winter. So you determine which one do you think is in winter. Okay, so the bottom one is actually the one that's in winter, and the top one is the one that's in summer. So again, gentle wave activity means that it's dominated by swash, dominated by material coming onto the beach. Whereas the winter time, it's dominated by backwash, meaning sediment being taken off of the beach. So you don't see the fine sand anymore, you just see the big rocks, right? The waves aren't going to take off these big rocks, but the waves can easily take off fine sediment. Okay, now waves don't just travel isolated from one another. So in this image here, you should see that there's an area where waves are actually meeting, right here. Okay, and so what we have here is what's called interference. And what that makes, what that creates, is that waves aren't usually uniform, right? So if you're sitting on a beach and you're watching a wave train, you're watching a set of waves come in, usually you'll see a big wave and then maybe a smaller wave and then a bigger wave, or three smaller waves and then a big wave or something like that, right? They're not uniform. They're not all the same size. And that's because waves cross over other waves. They are influenced by other waves. So when two wave trains meet, they can either add to each other or subtract from one another. And we call this interference. So destructive interference would be interference that subtracts from one another. So they come together and both of them get smaller. Constructive interference is where they add to each other. So two wave trains come together and you end up with bigger waves. For example, down here we have two waves that are interfering with one another. We have one red wave and one blue wave. Down here is the resulting wave that gets created. So you can see at this location right here, it's marked as a 1, the crest and the trough of the two waves are almost perfectly matching up. Therefore, they can add to one another and create a wave that is nearly twice as big as what they were. If you go over here, though, to position number 2, you see that the crest of one is matching up with the trough of another one. So therefore, they are subtracting from one another, and therefore you get a much smaller wave than what either of the two were before. So that would be called destructive interference. So again, constructive interference, the troughs and the crests match up perfectly. They add to one another, and therefore they create a much bigger wave. Destructive interference is where you have the crests, the troughs, and the crests meeting each other, right? So you have this one's trough meeting with this one's crest. You have this one's crest meeting with this one's trough. And if they are perfectly in line, then they completely cancel each other out, and you end up with flat water, essentially no wave. And again, that's called destructive interference. They are destroying each other. Another important thing to discuss when we talk about waves are rip currents. So you may have heard the term rip tide. Rip tide is a misnomer because a tide is actually something that's caused by gravity, essentially. So the term rip current is more appropriate. So as a wave comes in and breaks, some of the energy is reflected back out. Remember, we have waves come in and waves go back out. Okay, so sometimes, depending on the shape of the beach, all of the wave energy that comes in ends up going out in one specific location. And when that happens, we call that a rip current. Okay, it often forms when waves in one area are stronger than waves in another area. It also often forms in places where you have land jutting out around a coved beach. Okay, so basically the wave will come in all across that beach, but it will end up going back out all in a line. And so somebody's put dye in the water here so you can actually show where the rip current is. So essentially what's happening is this area would be dominated by the swash, and this area would be dominated by the backwash. Basically, water being pulled off of the beach. So if you're out swimming in this, right, the waves would probably help you come into the beach over here. But if you ended up in this, the water would actually take you farther and farther away from the beach. So what you should do if you end up with that happening is just to swim parallel to the beach. Don't try to swim back towards the beach. You'll just end up getting tired, and that's how a lot of people drown. So what you want to do is just swim parallel to the beach so that you can get out of the rip current and back into where the waves are moving back onto the beach, and then you can swim back onto the beach. Basically, the best thing to do is not panic and to relax and try to let yourself float. Sometimes, depending on the rip current, sometimes if you wait long enough, the rip current will actually bring you back in, and that's what a lot of the suggestions are starting to be in places like Australia, but not every beach is the same. So sometimes that rip current could take you for miles off of the beach. Okay, so just assuming that it's going to bring you back around eventually is probably not a good idea, because not all beaches are equal. So the best thing to do is just, you know, swim parallel to the beach. Don't panic, stay calm. You're going to get back, okay? Okay, and finally, a different type of wave is called a tsunami. Tsunami are not generated by wind. Instead, they are generated by sudden changes from land, essentially. Okay, so they can be generated by earthquakes, by avalanches, basically where you have a big bunch of land that falls into the ocean. They can be generated by a volcano in the ocean collapsing, or even from a volcanic eruption underwater. Okay, so essentially what happens is when an earthquake occurs, that earthquake pushes up on the water, right? And since a wave is just a disturbance that travels through a medium, that creates a disturbance in the water, and that creates a wave. That wave can then travel to distant shorelines and wreak havoc. And the reason why it wreaks havoc is because a tsunami ends up as a shallow water wave. So the wavelength is typically greater than 200 kilometers. So they can be felt to a depth of 100 kilometers deep. There's no place in the ocean that is 100 kilometers deep, right? That would be 100,000 meters, right? So it doesn't matter where a tsunami is traveling, tsunami is pretty much always going to feel the bottom. And therefore, as it approaches the shoreline and it feels the bottom, the wavelength decreases, and that causes the wave height to increase. But because the wavelength is so huge, the change in that wavelength is really drastic, and that can create a drastic wave height increase. So in the open ocean, they actually travel extremely quickly because of this huge wavelength. So they can travel 700 kilometers per hour, but their wave height is not very large. So if you are on a boat in the middle of the ocean and a tsunami went under you, you probably wouldn't even notice because the wavelength is so big. You wouldn't even notice because basically because the wavelength is so big, the steepness is very small. It's not a very steep wave, so you're not really going to feel it. But as the wave approaches the shore, the front wave slows down, the wavelength decreases, and the wave height increases very rapidly. And that can result in a surge of water that can be 30 meters tall. So that can create an extremely devastating situation. The pictures that I have here are from, I believe, Thailand. It was maybe around 2003 or 2004 where a tsunami hit. And you can see the picture before the tsunami hit and a picture after the tsunami hit. So you can see that huge well of water there. And the same tsunami ended up hitting multiple places around the Indian Ocean. Okay, if you have any questions, please post them on the weekly discussion. Thank you.